What happens when a wandering cosmic object decides not to leave? Most of us assume that interstellar objects are only passing visitors. They come from the space between stars, rush through the solar system at great speed, and disappear forever into the dark. They do not stop. They do not turn back. They have no reason to stay. In theory, 3I, Atlas, should be no different. It is the third confirmed interstellar object ever observed. It was not born in the solar system. Its trajectory is open, its velocity high. Everything about it suggests a single flyby, followed by permanent departure. Early observations seem to confirm exactly that, until attention shifted to one very specific moment. On October 29, 3I, Atlas will vanish from Earth's view, not because it is too far away, but because it moves directly into the sun's glare, a region where ground-based telescopes cannot safely observe. Under normal circumstances, this would mean nothing more than a temporary observational gap, a blind spot in the data. But according to Harvard astrophysicist Avi Loeb, this disappearance may be the most important part of the entire encounter. As it passes behind the sun, 3I, Atlas enters a region where solar gravity does more than simply bend trajectories. Under very rare conditions, that gravitational field can act like a sling, one capable of transforming a fleeting visitor into a bound object. No engines, no guidance, just mass, velocity, and geometry aligning precisely enough. And just as this possibility comes into focus, new data begin to change how we see 3I Atlas. Its estimated mass has been revised upward to at least 33 billion tons, far larger than previously thought. Its chemical composition does not follow familiar cometry ratios, and a faint green glow widely discussed appeared at a moment when standard models say it should not have been possible. None of this suggests intent. None of it proves control, but it forces us to abandon a long-held assumption that every interstellar object simply passes through. In rare cases, the universe may not only allow a traveler to enter it, may quietly close the door behind it. And that is where the real story begins. On the night of the 1st of July, that system recorded a source that did not match the usual patterns. The object was dim, not impressive to the eye. Yet, when positions were measured and compared over time, something stood out. Its path did not fit the patterns of long-period comets tied to the sun. The trajectory pointed to a different origin. Calculations of the orbit showed that this object was not bound to the sun. The curve it followed was open, not a closed loop. This visitor would pass through the inner solar system once, and then continue outward, never to return. By comparing its motion to the motions of planets and other small bodies, it became clear that it was moving too fast. On too open a track to have formed here. It was coming in from interstellar space. That made it only the third interstellar object ever identified passing through the solar system. Two earlier visitors had been spotted in previous years. One had no visible cloud of gas or dust, but showed a slight, non-gravitational push that raised many questions. The other looked much more like a normal comet, with a tail and chemistry similar to the icy bodies that circle the sun. 3I, Atlas, joined this very small group. But it was not simply a copy of either one. It was another data point from outside, carrying its own set of details and puzzles. Once it was clear that 3I, Atlas, came from beyond the solar system. Two simple questions organized the curiosity around it. What exactly was this object? And where was it on its path at each moment? From those two questions followed many smaller ones. How large was it? What was it made of? How did it react to sunlight and the solar wind? Each new observation was one more piece to place on a slowly forming picture. The year in which 3I, Atlas, was observed was already filled with unusual events and intense discussion about objects in space. Articles, preprints, interviews, and public debates accumulated around this particular visitor. It drew attention not only because of its interstellar origin, but also because early reports hinted at behavior that did not match the standard picture of a comet. Polarization of the light seemed unusually high. The shape of the surrounding glow looked strange. Estimates of its size shifted as more data came in. All of this unfolded against a background of growing public interest in space and in the possibility of technologies beyond Earth. In that climate, 3I, Atlas, became a kind of focal point. Some saw it as a chance to better understand how small bodies form around other stars. Others wondered if it might, in part, be artificial. Most of the basic orbital properties pointed toward a natural object. Its speed, though high, was in the range expected for debris moving through the galaxy. Its path through the solar system could be explained by gravity alone. Nothing in the large-scale motion forced a dramatic conclusion. At the same time, the details refused to line up neatly. Over time, a list of roughly 15 anomalies was collected from observations and analyses. These did not prove a technological origin, but they showed that the object did not behave like a typical solar system comet. The unusual jet aimed toward the sun, the strong and persistent anti-tail, the exact alignment of the spin axis, the high polarization of scattered light, and other features all pulled in that direction. Each one, taken alone, might be explained away. Taken together, they were harder to ignore. This combination of an ordinary-looking orbit with non-ordinary details placed 3I, Atlas, in an interesting position. The main doorway to understanding it still led through natural explanations: ices, dust, heating, and outgassing modified by geometry and time. At the same time, a side door was left slightly open. If a natural model could not account for the full set of observations, then more exotic possibilities would need to be considered carefully, rather than dismissed in advance. The situation resembled what are sometimes called black swan events. These are events judged very unlikely before they happen, but with consequences too large to ignore if they do. In many areas, from security to finance, ignoring such events has led to costly surprises. In this case, the cost of ignoring an interstellar object would not be direct damage, but a missed chance to learn something important about the universe and about the possible presence of technology beyond Earth. For that reason, 3I, Atlas, was treated as an opportunity to observe as much as possible, as precisely as possible. Throughout this process, the tone around the object slowly settled into a balanced one. On one side was the recognition that nature is often more varied than initial models suggest, and that unusual comets and asteroids exist even within the solar system. On the other side was a quiet reminder that, if any sign of non-natural engineering ever appeared, it would likely first show up as a collection of small anomalies in the data, not as a clear and simple message. The appropriate response was not excitement or fear, but patient, careful watching. Seen in this way, 3I, Atlas can be thought of as a test of method more than a test of belief. It asks how to handle an object that is mostly ordinary at first glance, yet carries enough irregularities to resist easy classification. It asks how much effort to invest in tracking a visitor that will soon be gone forever, and how open to remain to explanations that reach beyond familiar categories. As its path carried it closer to the sun and then away again, instruments continued to follow its light, its surrounding cloud, and the thin structures extending from it, adding more detail to the evolving picture. Long before any eyes on Earth could turn upward, 3I, Atlas, had already been moving through space for an immense stretch of time. It did not begin its journey here. The path and speed measured from its motion make that clear. The orbit is open, not closed. The object comes in, swings around the sun once, and then leaves, never looping back. This is not how a body born inside the solar system behaves. Most long-period comets, even the distant ones, are still tied to the sun by gravity, returning after long intervals. In contrast, The track of 3I, Atlas, shows no promise of return. It crosses the solar system as a visitor, not as a resident. When the orbit is traced backwards, the line does not point to any known family of comets or to the distant Oort cloud that surrounds the solar system. Instead, it stretches outward into the wider galaxy. The velocity, once corrected for the motion of the Sun through the Milky Way, matches the range expected for material drifting between the stars. It may have come from an older region of the galaxy, sometimes called the thick disk, where stars and their planetary systems formed long ago and follow orbits slightly different from those in the thinner, younger disk. In that picture, 3I, Atlas, is like a fragment knocked free from its original system, slowly carried along by galactic motion until it happened to cross the neighborhood of the Sun. It can be imagined as a small, ancient stone, once locked inside a larger body, some past event, perhaps a collision or a close encounter with a giant planet in its home system, would have given it enough energy to escape. Since then, it has been drifting in the thin gas between stars, where nothing much happens for long periods of time. There, the distances are so large and the densities so low that an object can travel for hundreds of millions of years without any dramatic change. Only when it finally approaches a star again does its path bend and its surface begin to respond to light and heat. The speed of 3I, Atlas, helps set the scale of this journey. Its typical space velocity is around 60 kilometers per second. For everyday experience, this number is hard to picture. It is much faster than any aircraft, faster even than most spacecraft leaving Earth. Yet, on galactic terms, it is modest. At that speed, crossing the thick disk of the Milky Way would take on the order of 1 billion years. That is 1,000 million years of quiet motion, through regions where stars appear only as distant points of light, and where the nearest solid surface might be many light years away. Thinking in these timescales changes the sense of the story. Human history, even when measured from the earliest known tools, covers only a few million years. Recorded history fits into a span of a few thousand years. Modern astronomy, with its sensitive telescopes and precise measurements, occupies just a few centuries. Against that backdrop, a billion-year journey is almost beyond direct intuition. For most of the time that 3I, Atlas, has been moving, the solar system, as it is now known, did not yet exist. The planets had not formed. Earth was not present as a solid world. Life, in any complex form, had not emerged on this particular planet. Only very recently, in the last thin slice of that timeline, did a species appear on a small rocky world orbiting the Sun, capable of building instruments, recording images, and calculating orbits. From the point of view of 3I, Atlas, this is a late development. The object has been in motion for hundreds of millions or billions of years. Humans have been able to notice such objects for only a brief moment at the end of that long track. The meeting between the two is therefore a coincidence in time, a crossing of paths between an old traveler and a young observer. A simple picture can help. Imagine a street party that has been going on all day in a neighborhood. Most neighbors have been there from early on. They know the music, the stories, the history of the gathering. Now, imagine someone who arrives just before the party ends. This latecomer can look around, see who is present, listen to a few conversations, but has missed most of what happened before. The solar system, with its planets, comets, and asteroids, has been part of a long-running gathering in the galaxy. Objects like 3I, Atlas have been moving through this environment for ages. Humanity, as the late arrival, is only now trying to understand what has been happening all along. In this larger neighborhood, some members are far more influential than others. One planet in the solar system, a gas giant more than 300 times the mass of Earth, dominates the gravitational landscape beyond the inner region. It shapes the orbits of many smaller bodies, captures some, and ejects others into new paths. For most of the age of the solar system, such processes have been at work without any observers to record them. Only now, with the presence of instruments and analysis, is there a chance to see an interstellar object interact with this network of forces in real time. Recognizing this timing helps soften the idea that human concerns should sit at the center of the story. The object does not adjust its path to visit Earth. It does not slow down to be examined. It follows the line drawn for it by gravity over immense stretches of time. The fact that it passes through the inner solar system during the brief era when there are telescopes here is noteworthy, but it does not change the underlying scale of its journey. In this sense, the arrival of 3I, Atlas, is more a reminder of how young the observing species is, rather than a sign that the object is aimed at it. From a scientific point of view, the classification of 3I, Atlas, as an interstellar object is almost straightforward. The orbit is hyperbolic. The incoming speed relative to the Sun matches expectations for material drifting in the galactic potential. The direction of approach does not point back to any known source inside the solar system. On that level, the conclusion is simple. This is a visitor from beyond, in that limited sense. Some researchers have referred to it as a no-brainer. The main question of origin does not require elaborate reasoning. The interstellar nature is written into the basic motion. However, simple at one level does not mean simple at all levels. The confidence in its status as an interstellar object says nothing, by itself, about its detailed makeup or history, the surface structure, the internal composition, the exact way it responds to sunlight, and the patterns seen in its surrounding cloud of gas and dust are all separate layers. These layers contain the anomalies and subtleties that make 3I, Atlas, scientifically interesting. The clear label of interstellar is only the outermost tag. Beneath it, the object remains complex and, in many respects, unfamiliar. This is where the story starts to branch. On one branch, the goal is to explain every observed feature through natural processes: ice turning to gas, dust carried along with escaping material, forces from sunlight, and the shaping effect of the solar wind. On another branch, there is a cautious awareness that, in principle, the galaxy could also contain devices or debris of technological origin. If such things exist, they might also travel between stars and might, at first, appear as small, strange points of light moving through the sky. For that reason, the presence of repeated anomalies in the data cannot be dismissed lightly. In practice, this means that 3I, Atlas, is approached as a kind of layered puzzle. The first layer, the orbit, is largely solved. It is a passing visitor from beyond the solar system. The deeper layers are still being worked through. Each new measurement adds a piece to a mosaic that is not yet complete, while the dominant expectation remains that it is a natural fragment of rock and ice. Its long history through the galaxy and the late timing of its encounter with human observers give it an extra weight. It becomes not just another comet, but a rare sample of matter shaped in another part of the Milky Way, arriving at a moment when there is finally someone here to notice. Sometimes, an object from far away passes through Earth's orbit without even turning its head. It does not slow down, does not send a signal, does not change course. It simply follows its path. That is how 3I Atlas crossed the region near our planet. As it moved inward, its distance to the Sun decreased until it reached its closest point at the end of October. On that day, the object passed perihelion, the moment of minimum distance to the Sun. Weeks later, in mid-December, it reached its closest approach to Earth. These dates marked key points in its track through the inner solar system. They could have been occasions for drama, if the object had done anything unusual. Instead, The motion remained smooth and quiet. The orbit could be calculated from repeated position measurements over time. Each new data point fell neatly along the curve predicted by gravity alone. There was no sign of sudden maneuvers. No small sideways jumps. No unexpected changes in speed. The path of 3I, Atlas, was that of a body responding to the pull of the sun and the planets. Nothing more. In popular imagination, an interstellar visitor passing near Earth might adjust its trajectory, as if to take a closer look. For 3I, Atlas, nothing like that appeared in the data. As it went through perihelion, its direction evolved exactly as orbital mechanics dictate. When it passed the point of closest approach to Earth, the same calm pattern continued. Distances changed, angles shifted, but always in a way that matched the expectations of a natural object moving through a known gravitational field. This behavior is important. It sets a baseline. If there had been large, unexplained accelerations during these key moments, they would have stood out sharply against the predicted orbit. Any departure from the usual gravitational curve would have been flagged immediately. The absence of such features tells a simple story at the large scale. The trajectory itself is ordinary. Whatever is unusual about 3I Atlas must lie in other layers, not in the broad shape of its motion around the sun. Even so, the period around perihelion brought its own challenges for observers. As the object approached the sun, its apparent position in the sky moved closer to the solar glare. Seen from Earth, it slid into a region of the sky where the angular separation from the sun was less than about 30 degrees. For ground-based telescopes, this geometry is difficult. The bright atmosphere near sunrise or sunset, combined with the direct brilliance of the sun, overwhelms faint sources. In practice, this meant that just when 3I Atlas was closest to the sun, it became hard or impossible to see from Earth's surface. Instruments that need dark skies could not safely point so near the sun. Sensitive detectors would have been flooded with scattered light. Even for space observatories, observing near the sun involves careful planning and strict limits. As a result, there is a natural blind spot in the record. This blind spot is a matter of simple geometry and instrument safety, not secrecy. Sometimes, an object can be physically close and yet effectively invisible, hidden not by distance but by brightness. In this case, the object did not vanish in a mysterious way. It moved into a region where the line of sight from Earth ran too close to the sun for regular tracking. As it moved on and the angle widened, it gradually emerged again into view. Accepting these gaps in the data is part of understanding how observation works. The absence of continuous coverage does not, by itself, suggest strange behavior. It simply reflects the fact that measurements depend on vantage point and conditions. For 3I, the segments of the orbit that were well observed line up smoothly with those that were not. Once the object returns to a safer angular distance from the sun, the reconstructed path does not require hidden maneuvers to connect the dots. When the object passed near Earth in December, attention returned to the question of whether there might be any sign of active control. An interstellar craft, if it existed, might be expected to perform some kind of course adjustment when passing through a planetary system. It might fine-tune its trajectory, slow down to examine a planet, or change direction to enter orbit. All of these would leave fingerprints in the form of non-gravitational accelerations. The measurements around closest approach, however, show no such fingerprints. The position and velocity of 3I Atlas continue to follow the same predictable curve. The only forces needed to explain the motion are gravity and the small, steady effects of outgassing and solar radiation, both of which can be modeled as gentle pushes rather than sharp thrusts. There are no abrupt kinks in the trajectory, no sudden changes in momentum. This calm behavior pushes the interpretation further toward a natural origin, a non-rotating rock of ice and dust, heated by the sun, will emit gas and dust in a way that can sometimes alter its path slightly. These changes tend to be gradual and can often be captured by introducing small correction terms into the orbital equations. That is the kind of adjustment seen with many comets. The motion of 3I, Atlas, fits comfortably within that framework, without needing any large or sharply timed impulses. At the same time, the absence of dramatic motion does not empty the object of interest. It simply clears the stage at the level of orbit. With the large-scale track behaving as expected, attention can shift to other, more subtle aspects: the shape and direction of the jets, the structure of the surrounding cloud, the way light is scattered and polarized, the alignment of the spin axis, and the timing of changes in brightness. These are the domains where the anomalies live. Seeing 3I, Atlas glide through the inner solar system without performing any visible dance near Earth also reinforces a more general point. Not every interstellar visitor is centered on human concerns. Most will pass through without reacting to the presence of an inhabited planet at all. The role of observers, in this case, is not to be the target of the event, but to be a silent witness. The object continues on its way. The instruments record what they can. The rest is interpretation. As the days of closest approach passed, 3I, Atlas, moved slowly outward again, gaining distance from both the Sun and Earth. The geometry changed once more. The angle between object and Sun increased. Observational conditions improved. Telescopes could follow the fading light for a time, tracing the retreat along the exit branch of the orbit. Again, the measured positions sat where the gravitational model predicted they should be. By the time it left the inner solar system, the main story of its passage near Earth was complete. There had been no sudden turns, no braking, no loops or halts. The closest points in distance had come and gone without any sign of active steering. What remained was a set of trajectories and brightness measurements that could be used as a clean reference frame. Against that quiet background, the more unusual details in the shape of the coma and tail would stand out more clearly. In that sense, the silent flyby near Earth was not a disappointment, but a useful anchor. It showed that, at least at the level of bulk motion, 3I Atlas behaved like a natural object. That allowed the focus to move, step by step, toward the finer structures that made it special. The narrow stream of material pointing toward the Sun, the persistent anti-tail, the fixed alignment of its jets, and the rhythmic changes in its light. At first glance, the brightness of 3I Atlas made it look enormous. If all the light recorded from it had come from a single solid surface, the object would have needed to be about 20 kilometers across. That is roughly the size of Manhattan, or of the impactor, thought to have ended the age of the dinosaurs about 66 million years ago. On paper, it looked as if a Manhattan-sized fragment from another star system had entered the inner solar system. That first estimate carried weight. An interstellar body of that size would be extremely rare. A rock or icy nucleus 20 kilometers wide would hold a vast amount of mass and energy. If such a body were ever on a collision course with a planet, the consequences would be catastrophic. Even without any danger to Earth, the very existence of such a large interstellar object would challenge ideas about how material is formed and ejected around other stars. For a short time, the numbers suggested that something on that scale might be drifting past. Later observations began to separate the different sources of light in the image. By looking more closely at the structure of the glow around 3I Atlas, it became clear that most of the brightness did not come from a bare, rocky or icy surface. Instead, the majority of the light originated in a cloud of gas and dust surrounding the nucleus. That cloud, called a coma, scattered sunlight over a much larger area than the core itself could ever present to the Sun. In detailed images, the central pixel containing the nucleus contributed less than 1% of the total light. The rest came from the extended, diffuse region around it. This changed the picture, rather than a single, massive block 20 kilometers across. The object was now better understood as a much smaller central body wrapped in a broad, luminous envelope. The Manhattan in space image gave way to something more subtle, a compact core hidden inside a glowing cloud. This shift carries an important lesson. Brightness alone does not translate directly into size. When a small body is surrounded by gas and dust, the illuminated material can make the entire system appear much larger than the nucleus really is. Any estimate that treats all the light as reflected from solid rock will overstate the dimensions for objects like 3I Atlas. The coma has to be accounted for before reliable conclusions can be drawn about the actual bulk of the core. Once the coma is recognized as the main source of light, attention naturally turns to what it is made of. Spectroscopic observations, which break the light into its component colors, reveal the fingerprints of different molecules. In the case of 3I Atlas, these fingerprints pointed to an unusual chemical balance. The amount of methanol detected in the gas was roughly 100 times higher than the amount of hydrogen cyanide. Cyanide itself was clearly present as well. Methanol is an organic molecule often found in comets, but the ratio relative to hydrogen cyanide in this case stood out. The pattern did not match the typical mix seen in many solar system comets, which are often rich in water and show different relative line strengths. The gas around 3I Atlas looked like a distinct blend, as if it had been assembled in a different kind of chemical kitchen. The presence of cyanide, a substance used as a poison in past wars on Earth, added a layer of public curiosity, even though the real situation in space is governed by dilution and distance. This unusual chemical ratio hints at a formation environment that does not mirror the familiar outer regions of the solar system. The conditions in the disk where 3I Atlas formed may have favored certain ices over others, producing a composition that now reveals itself in the coma. In that sense, the gas surrounding the object is more than just a byproduct of warming. It is a sample of the chemistry of another planetary system, carried into the inner solar system and made visible by sunlight. The detection of cyanide naturally led to a practical question. Could any of this material reach Earth in dangerous amounts? To address this, estimates of mass loss from 3I Atlas were combined with what is known about the solar wind and the geometry of the orbit. The flow of gas away from the nucleus spreads out into space, but it does not move freely. Charged particles from the sun, streaming outward as the solar wind, interact with the escaping gas and push it away. Calculations using the observed rate at which 3I Atlas was losing mass suggested that the gas would be swept aside within a few million kilometers of the object. That is a large distance in human terms, but small compared to the scales involved in planetary orbits. At its nearest, the path of the object passed roughly 50 million kilometers from Earth's orbit. In effect, the region where the cyanide-bearing gas could exist at any meaningful density never came close to the path of the planet. One way to picture this is to imagine narrow streams of gas being released and immediately caught by a strong, outward-blowing wind from the sun. The streams are pulled away from the object and thinned out long before they could intersect the track that Earth follows. By the time the gas would even approach that distance, it would be too diffuse to have any noticeable effect. The conclusion is simple. There was no realistic risk of toxic gas from 3I Atlas reaching Earth during this passage. Beyond gas, there is also the question of dust and larger particles. The coma and tail of a comet-like object often contain a range of solid grains, from tiny specks to larger fragments. For 3I Atlas, models of the dust environment considered how particles of different sizes respond to radiation from the sun. Very small grains, smaller than about 1 micron, feel a strong push from sunlight. Radiation pressure drives them rapidly away. bending their paths outward and clearing them from the vicinity on relatively short timescales. Larger grains, bigger than about a millimeter, are less affected by radiation pressure. Their motion is dominated by gravity. Some of these larger particles can, in principle, cross Earth's orbit at a later time, depending on the exact geometry. For those, the key factor is size. Objects smaller than about 1 meter in diameter generally burn up in the atmosphere if they enter at cosmic speeds. They produce shooting stars or bright fireballs, but do not reach the surface intact. Taking into account the total mass lost by 3I, Atlas, during its passage, and the distribution of that mass among different particle sizes, the number of large fragments capable of surviving all the way to the ground is expected to be negligible. Most of the debris either gets pushed outward by light, or, if it ever intersects Earth's path, is consumed in the upper atmosphere. The idea of a heavy interstellar rain reaching the surface of the planet from this event does not match the available numbers. Putting gas and dust together, the direct physical risk to Earth from 3I, Atlas in this encounter is essentially zero. The object released material into space, as many comets do, but the solar wind and the vast distances involved prevent that material from concentrating near the planet in harmful ways. Rather than being a delivery of dangerous substances, the outgassing acts more as a tracer, making the object easier to study and turning its composition into a visible signal. With these points settled, the focus can shift away from concern about immediate effects and back toward the deeper scientific interest. The brightness that once suggested a giant solid body is now understood as the glow of a broad coma around a smaller nucleus. The chemical makeup of that coma, with its unusual methanol to cyanide ratio, points to a different birthplace and history. The dust and gas form structures that reveal how the object interacts with sunlight and the solar wind. All of this information turns 3I, Atlas, into a detailed case study of interstellar material, not a threat, and sets the stage for examining the strange geometry of its tail and jet in even greater depth. After passing the orbit of Earth without pausing, 3I Atlas kept sliding outward. The Sun slowly grew smaller behind it. Ahead, another gravitational presence waited. The object was now on a path that would take it into the domain of the largest planet in the solar system. If the motion continues as predicted, 3I Atlas will come closest to Jupiter around the middle of March 2026. The distance at that point is expected to be about 53.5 million kilometers. On the scale of the solar system, that is not a close encounter, but it is near enough for Jupiter's gravity to matter. As the object moves into that region, the pull from the giant planet gradually becomes more important compared to the pull from the Sun alone. This part of the journey takes place far from the inner planets. The object moves away from the heat and light that shaped its activity near perihelion. The coma thins. The jets, if still present, weaken under the reduced energy from the Sun. At the same time, a different kind of influence grows. The shape of the path begins to feel the subtle tug of Jupiter. The story that started near Earth's orbit now continues in a quieter, more distant arena. There is a useful way to describe the region around a massive planet. At some distance from the planet, its gravity and the tidal pull of the Sun balance in a particular way. Inside that distance, the planet can effectively hold on to small bodies in stable orbits. Outside it, the Sun's influence dominates. This boundary is called the Hill radius. For Jupiter, because of its great mass, the Hill radius is large. The region where its gravity rules is wide compared to that of other planets. On its way outward, 3I, Atlas, will pass through this gravitational territory. It will not come close enough to be captured, but it will cross the zone where Jupiter's influence is stronger than the tides from the Sun. The object simply traverses this region as part of its open orbit. Yet the fact that it does so is one more detail added to the overall picture. It is as if the visitor walks through the edge of another giant's courtyard before leaving the neighborhood entirely. For most small bodies, this is just how the mechanics of the solar system work. Many comets and asteroids pass through the Hill sphere of planets without incident. Some are perturbed into new orbits. A few are captured as temporary moons. Others are flung outward on different trajectories. For 3I Atlas, the expectation is straightforward. The path should be slightly bent by Jupiter's pull, but remain unbound, continuing outward after the encounter. Still, the combination of an interstellar origin and a passage through such a significant gravitational zone makes this part of the track worth noting. If anything unusual were ever to happen to the orbit, this would be a natural place to look. A sudden change in direction near Jupiter, unexplained by known forces, would be hard to miss against the predicted curve. In reality, the simplest expectation is that the object will move through the Hill region smoothly, without sharp deviations. Around massive bodies like Jupiter, there are also special points where gravitational forces and orbital motion come into balance. These are known as Lagrange points. At these locations, a small object can remain in a relatively stable position with respect to the planet and the Sun, or slowly orbit around such a point with little expenditure of energy. Some are located ahead of and behind the planet in its orbit. Others lie along the line connecting the planet and the Sun. In the Earth-Sun system, one of these points, called L2, lies on the night side of Earth. A large space telescope has been placed there to take advantage of the stable environment and the continuous view of deep space with minimal interference from the Sun and Earth. Similar points exist in the Jupiter-Sun system. They are natural parking spots in space, where spacecraft can hover using relatively small amounts of fuel. These concepts are relevant whenever the possibility of technology is discussed. If any advanced civilization were to place devices in another planetary system, regions like Hill spheres and Lagrange points would be natural candidates. They offer long-term stability and wide views. The fact that 3I Atlas passes through Jupiter's gravitational sphere and through a sky that contains these special locations does not by itself prove anything about its nature. It simply provides context. The geometry is compatible with many ordinary scenarios and a few more speculative ones. For this reason, the segment of the orbit near Jupiter is treated as a kind of checkpoint. Up to now, the motion of 3I Atlas has looked normal at large scale. The orbit is hyperbolic. The flyby near Earth showed no sudden thrusts. The strange features have appeared mainly in the shape of the coma and tail, in the polarization of light, and in the detailed geometry of the jets. As the object approaches Jupiter's domain, the question is whether any new irregularities will show up in the way the orbit bends. If the object moves through the region exactly as gravity predicts, without extra accelerations or sharp turns, that will strengthen the case that it is entirely natural. Interstellar origin would remain, but with fewer reasons to suspect additional layers. The list of anomalies would still be there, but they would be tied more to surface physics and geometry than to any sign of active control. In that situation, the interpretation would shift further toward a complex, but non-technological, comet-like body from another system. On the other hand, if unexpected changes in motion are detected in this phase, they would require careful analysis. Small deviations could come from outgassing, from uneven jets of gas acting like tiny thrusters. Larger, sharply timed changes would be harder to explain without invoking non-gravitational forces of a different kind. The data from this passage, once fully collected and processed, will help narrow the range of plausible stories that can be told about 3I Atlas. This approach reflects a general way of updating understanding. When an object is first discovered, many possibilities are open. As more data come in, some are ruled out, others remain. Confidence in any specific explanation grows or shrinks depending on how well it fits new observations. For 3I, Atlas, the broad expectation is that if nothing unusual happens near Jupiter, the view of it as a natural interstellar object will become more secure. Until that segment of the trajectory is fully observed, however, the situation stays open. The object continues along its path, slowly leaving the inner solar system and entering the outer regions. Instruments follow it as long as brightness and geometry allow. Each new measurement near the time of closest approach to Jupiter adds another point to the curve. The gravitational boundary around the giant planet is not a stage for sudden revelations yet. It is, instead, a stretch of space where quiet, careful tracking can either confirm what is already suspected or suggest that something more is happening behind the familiar pull of gravity. Even if 3I, Atlas, is ultimately classified as a normal interstellar comet, it still acts as a special case. It gathers around itself a collection of questions large enough to influence how observation and analysis are done. It is not just another point of light to be catalogued and forgotten. It is a reminder of how much can be hidden inside a single object that passes briefly through the field of view. Over time, observers have identified a list of roughly 15 unusual features connected with 3I, Atlas. Each one, on its own, might not be decisive. Together, they form a pattern that does not fit easily into standard models of comet behavior. The unusual geometry of the jet, the strong polarization of the light, the alignment of the spin axis, the timing of brightness changes, and other details all contribute to this list. None of them, taken alone, prove that the object is artificial or extraordinary in any dramatic sense. Yet, as a group, they mark it as a case that deserves serious attention. This is where the idea of a black swan becomes useful. A black swan event is something considered very unlikely, but carrying consequences too large to ignore if it turns out to be real. In many areas of human activity, institutions have suffered because they dismissed rare scenarios that later unfolded with great impact. In hindsight, warning signs were visible, but either not collected carefully or not treated as important. The lesson is simple. Low probability does not always mean low priority. Applied to 3I, Atlas, this means that even if the chance of a technological origin is small, the potential implications are so large that careful data gathering is justified. The cost of tracking the object, taking spectra, and modeling its motion is modest compared with the value of the information gained. If it is natural, the result is a better understanding of how interstellar comets form and behave. If it showed any clear sign of artificial design, the impact on science and culture would be profound. Either way, ignoring those 15 anomalies would not be a responsible option. In contrast, there are many areas of research where the stakes are different. Some high-energy physics experiments search for particles that may or may not exist, such as hypothetical versions of neutrinos. When results show no signal, the outcome is still interesting for specialists. It tightens the allowed range of theories. However, the presence or absence of those particles has little immediate effect on daily life. Most people never notice whether such a discovery was made or not. The case of 3I, Atlas, belongs to a smaller group of topics where the outcome reaches beyond a narrow field. The question of whether any technological activity exists beyond Earth is not just a technical point. It touches the way humanity understands its place in the universe. A clear answer, even if it is negative, shapes expectations about the rarity of life and intelligence. A positive indication would reshape many long-held assumptions. For that reason, an object that might carry hints in that direction occupies a special role. Even if all the data eventually line up in favor of a natural explanation, the process of checking carefully has its own value. It demonstrates a way of handling uncertainty, open to surprising possibilities. but anchored in measurements. Information is not filtered to fit preformed beliefs, either skeptical or enthusiastic. Instead, each observation is taken as one more point in a growing pattern. For an interstellar object that could have been dismissed as just another comet, this approach sends a quiet message about how seriously rare events should be treated. There is also a human side to the story. When news and discussions about 3I, Atlas, began to spread, they reached far beyond technical journals. Families, students, and people outside science paid attention. Some parents wrote to say their children had started asking questions about the stars. Teachers reported that students were suddenly more engaged when topics like interstellar visitors appeared on the board. The idea that material from another star system was passing through the solar system captured imaginations. Children who had once associated space mostly with rockets or simple images of planets began to ask different kinds of questions. Instead of only wondering if unidentified lights in the sky might be unknown craft, they started to think about what the universe sends through natural processes. What kind of systems produce objects like this? How often do they pass by? Could samples from other planetary systems be studied in detail one day? These questions are more precise, yet still full of wonder. Public figures, educators, and science communicators noticed this shift. Discussions of 3I, Atlas, became a useful starting point for explaining orbital mechanics, spectroscopy, and the structure of the galaxy in understandable terms. A single object, moving silently through space, turned into a focus for renewed interest in astronomy and space exploration. The details of jets and polarization, which might seem dry on paper, became part of stories that connected deeply with curiosity about origins and possibilities. In this way, the impact of 3I, Atlas, goes beyond the specific scientific outcome. Even if every anomaly can eventually be explained by natural physics and chemistry, the object has already performed another function. It has acted as a signal flare for attention, drawing eyes and minds toward the sky. It has reminded people that there are still unsolved puzzles passing overhead, and that careful observation can transform faint points of light into detailed knowledge about distant environments. From the perspective of scientific practice, 3I, Atlas also acts as a training ground. It forces teams to refine methods for rapid follow-up of interstellar objects, to improve coordination between observatories, and to think in advance about what kinds of measurements matter most when a rare visitor appears. The next time a similar object is discovered, there will be protocols in place that grew directly out of the experience with this one. Instruments will be ready. Questions will be better framed. In summary, 3I, Atlas, is worth following not only because it is unusual, but because of what it represents. It is a test of how seriously low probability, high-impact possibilities are taken. It is an example of how a single case can guide improvements in observation, modeling, and communication. It is a source of genuine curiosity for people who may never read the technical papers, but who still look up at the night sky and wonder what passes between the stars. In most comets, the tail is pushed away from the sun. Light and charged particles stream outward, and dust and gas are driven back like smoke in a steady wind. With 3I, Atlas, some of the most striking images told a different story. In them, a narrow feature stretches not away from the sun, but toward it, as if the material is flowing upstream. One key image came from a space telescope observation in late July. On the raw frame, a bright streak could be seen extending roughly twice as long as its width, aligned in the general direction of the sun. At first, this ratio did not seem extreme, but once the geometry of the viewing angle was corrected, the true proportions emerged. The structure was not just twice as long as it was wide. In physical space, it was closer to 10 times as long. What the camera had captured was not a stubby plume, but a slender jet. It helps to picture this feature as a thin, luminous thread. The nucleus sits at one end. From it, A straight, narrow line of light reaches inward, pointing back toward the source of illumination. Instead of the usual fan of material streaming away from the sun, there is a focused stream that seems to reach toward it. This runs against the basic intuition formed from decades of images of ordinary comets. It is the first clear sign of a major geometric anomaly. Measurements of its extent indicate that the jet stretches for about 1 million kilometers. That is roughly 2.5 times the distance from Earth to the Moon. Yet the width of the structure is much smaller than that, giving it a long, needle-like appearance. If Earth itself were to emit a similar jet, it would extend far beyond the orbit of the Moon, forming a bright line across the local space, while remaining remarkably thin. The combination of length and thinness is what makes this feature extreme. Short plumes near comet nuclei are common. Broad tails pushed away from the sun are also common. But a million-kilometer structure, narrow enough to appear almost as a straight line, and directed toward the sun, is far from typical. It suggests a mode of gas and dust ejection that is both highly organized and sustained. Just as important as the shape is the persistence. This anti-tail does not appear in a single image and vanish in the next. Observations over months show the same basic feature, always present, always pointing approximately toward the sun. Even in images taken at the end of November, the narrow inward-pointing jet remains one of the most recognizable characteristics of 3I, Atlas. It is not a fleeting flare or a momentary alignment. It is a stable part of the system. Such stability is hard to explain away as a brief disturbance or an artifact of measurement. Instrumental errors tend to vary from image to image. Short-lived bursts of activity on a comet's surface tend to change as the object rotates or as local ice supplies are exhausted, a structure that remains in place over many weeks. Keeping its orientation relative to the sun implies an underlying mechanism that is steady and repeatable over time. In the catalogue of known comet behavior, apparent tails pointing toward the sun do appear from time to time. Most of these are illusions created by perspective. When observers on Earth look along the plane of a comet's orbit, the dust tail can seem to overlap the line toward the sun, even though the particles themselves are still being pushed away. Changes in viewing angle can cause the tail to appear to swing from one side to another, giving the impression of odd directions that vanish once the geometry is properly understood. In other cases, brief anti-tail-like features can arise from particles moving in complex ways within the comet's orbital plane. As the comet passes through different positions, sheets of dust can line up with the line of sight, creating spikes or fans that seem to point inward. However, such configurations usually do not last long. The constant action of radiation pressure and the solar wind quickly bends most extended features back into the familiar direction. Away from the sun, what makes 3I Atlas stand out is that the inward-pointing jet is not merely an effect of projection. Analyses that take into account the three-dimensional geometry of the orbit and the line of sight still find the jet aligned toward the sun. Its length, thinness, and persistence all resist explanation as a simple viewing artifact. This places it in a very small class of observed structures, perhaps even on its own. To understand why this is puzzling, it is useful to consider what normally happens when ices near the surface of a small body heat up and turn to gas. If there is a patch of ice exposed on a rocky surface, sunlight warms it and molecules begin to escape. In the absence of strong constraints, the gas flows out in a roughly hemispherical pattern, spreading out as it moves away. Dust carried along with the gas follows similar paths. The resulting cloud is broad, more like a puff of mist than a sharp beam. After the gas and dust leave the immediate vicinity of the surface, sunlight and charged particles from the sun continue to act on them. The solar wind pushes charged particles outward. Radiation pressure nudges small grains away from the sun. Over distance, these effects tend to spread and bend the material. smoothing out any initial structure and aligning it with the usual tail direction. The natural result is a wide, diffuse feature, not a sharply defined, inward-pointing jet. In the case of 3I, Atlas, the narrowness and alignment of the jet suggest that the material is being guided or confined in some way. Instead of expanding freely in all directions, the flow appears to be collimated, kept within a narrow channel. One way to picture this is to imagine a fog machine versus a thin nozzle. A simple ice patch behaves like a fogger, filling space in front of it with a cloud. The observed jet behaves more like a well-aimed stream. This leads to a central question. What could be acting as the nozzle? One natural possibility is related to surface features. If volatile ices are located at the bottom of a deep pit or inside a narrow crack, sunlight might only reach them when it shines almost straight down. The walls of the pit could then act like the sides of a tube, forcing the gas to flow upward in a confined column. In that scenario, the collimation comes from the shape of the terrain. Even with this picture, there are difficulties. For the jet to maintain its long, straight form and its alignment toward the sun over months, the geometry would need to be very specific. The pit, or channel, would need to be positioned so that the sun remained near the same direction relative to it through a significant part of the orbit. The rotation of the nucleus, the changing distance from the sun, and the shifting angles involved would all have to work together to maintain the effect. The observed behavior raises the possibility that more than one active region, or more than one structural feature, is involved. It might be that activity from different parts of the surface contributes at different times, combining to produce a jet that appears steady on long timescales. Or it might be that the interior structure of the material, its porosity or layering, affects the way gas escapes. These ideas remain areas for modeling and simulation. What remains clear is that the antitail of 3I, Atlas, is not easily folded into the usual mental image of a comet. It points toward the sun, stays narrow over enormous distances, and persists across many observations. It is not a brief trick of perspective, but a recurring element of the object's appearance. As such, it becomes one of the key features that any complete explanation of 3I Atlas must account for, and it opens naturally into further questions about spin, surface shape, and internal structure that lie ahead in the story. Most of the attention around 3I Atlas began with its strange tail. But the way the object spins is just as unusual. The rotation is arranged in such a way that, for 3I, the sun acts almost like a fixed lamp in the sky, shining down on the same side over and over again. Measurements of the jet direction over time show that it wobbles only slightly, by about 8 degrees around a preferred axis. That preferred axis, in turn, points almost straight toward the sun. In simple terms, the spin axis of the object is nearly lined up with the direction of sunlight. If that alignment were perfect, one half of the surface would face the sun all the time, and the other half would remain in darkness. Day and night would not alternate. One hemisphere would live in permanent day, the other in permanent night. 3I Atlas does not reach a perfect alignment, but it comes close. The small 8-degree swing is enough to introduce a little motion, but not enough to bring a normal cycle of sunrise and sunset to most of the surface. It is easier to imagine a small world where one side is always lit, with the sun hovering near the same point in the sky, moving only slightly back and forth. The opposite side never sees direct light at all. Between them lies a narrow band where the sun skims the horizon. This is very different from what happens on most rotating bodies, on Earth, and on many other objects. The spin axis is tilted relative to the direction of light. As the body turns, every point on the surface takes its turn, facing the star and turning away from it. Day follows night in a steady rhythm. For 3I Atlas, the geometry breaks that pattern. Rotation does not bring the sun into view for the dark side, and does not hide it from the bright side. The usual alternation is replaced by a stark divide. Such an arrangement is not required for an interstellar object. There is no obvious reason for a body arriving from another part of the galaxy to have its spin axis aligned with the sun in this particular way. Most random orientations would produce an angle with the incoming light that gives some kind of normal day-night cycle. The fact that 3I Atlas ends up in this special configuration counts as another geometric coincidence in a growing list. The behavior of the jet seems to be closely tied to this geometry. When the object was on its way in toward the sun, the main jet appeared to originate near one of the poles of the spin axis. It pointed roughly toward the sun from that region, following the same direction as the axis itself. As the object moved past perihelion and began to travel outward again, the active region appeared to switch. The jet now seemed to rise from the opposite pole, still pointing toward the sun. A simple way to picture this is to think of two active caps on the surface, one at each end of the spin axis. When one cap is slightly tilted toward the sun, it heats up and releases gas. The resulting jet then has a strong component in the sunward direction. As the geometry slowly changes along the orbit, the other cap takes over when it becomes the one more directly exposed to light. From an outside viewpoint, the jet seems to jump from one pole to the other, but in both cases, it continues to line up approximately with the sun. This pattern is not naturally produced by random patches of ice scattered across the surface. If volatile material were distributed without any special preference, the activity would tend to appear wherever local conditions happen to favor it, not concentrated near the poles in a symmetric fashion. The observed polar switching suggests some kind of structure or arrangement that links the locations of the activity to the rotation axis itself. One possible natural explanation brings surface features back into the picture. If the main ice reservoirs lie at the bottoms of deep pits or within narrow shafts, the geometry of those features could control when and how sunlight reaches the volatile material. Imagine a circular hole or a vertical crack in the surface. As the sun shines on the region, its rays can only reach the deepest part when they come almost straight down. At other angles, the walls of the feature keep the light out. When the sun is nearly aligned with the spin axis, and the pit sits close to one of the poles, there are moments when this straight-down condition is satisfied. The floor of the pit warms, and gas begins to escape. The rising flow is confined by the walls, so instead of spreading out sideways, it is forced upward as a column. In this analogy, the feature acts like a chimney. Only when the light shines nearly along the chimney's axis does the gas flow strongly. The result is a collimated jet that follows the same general direction as the incoming sunlight. This picture can, in principle, explain both the narrowness of the jet and its alignment. It also scales naturally to two poles if there are similar structures at both ends of the spin axis. When one pole is favored by the changing geometry of the orbit, its chimney becomes active. Later, when the other pole is better aligned, the roles reverse. In this way, the complex behavior of the jets could emerge from a combination of surface topography and rotation. At the same time, the constraints are quite strict. The pits or shafts would need to have the right depth and shape. They would need to be located very close to the poles. The spin axis would need to remain close to the direction of the sun over an extended part of the orbit. Any significant tilt or wobble would change the lighting conditions at the bottoms of the pits and could weaken or break the collimation. These requirements do not make the explanation impossible, but they do remind us that the situation is finely tuned. Another piece of evidence about the rotation comes from changes in brightness over time. Photometric observations show that the total light from 3I Atlas does not stay perfectly steady. Instead, it fluctuates in a regular way, with a period of about 16 hours. The amplitude of the variation is around 20%. That is, The object's apparent brightness rises and falls by roughly 1/5 of its average value on this schedule, repeating again and again. One early interpretation suggested that an elongated solid nucleus, rotating in space, might be responsible for this pattern. If a cigar-shaped body turns, the cross-sectional area facing the observer changes. Sometimes the long side is visible, making the object seem brighter. At other times, only the narrow end is seen, and the light drops. This kind of explanation works for many rotating asteroids and comets. The problem here is that, in 3I, Atlas, the nucleus contributes less than 1% of the total light. With the nucleus adding so little to the overall brightness, changes in its apparent size cannot account for a 20% variation. The main source of light is the coma and the jets, not the solid core. That means the regular 16-hour pulse must be coming from changes in the gas and dust distribution, rather than from direct viewing angles on the nucleus itself. A more consistent picture is that the jets are moving slightly as the object rotates, sweeping through different directions relative to the observer and to the sun. As the jet leans a little one way or another around the spin axis, the density and illumination of the coma in our line of sight change. When the jet is oriented in a way that sends more material into the region we can see, the brightness rises. When it shifts away, the brightness falls. The steady repetition of this motion would then produce a kind of heartbeat in the light curve. Seen this way, the 16-hour cycle becomes a signature of the rotation and jet geometry combined. It is not a random flicker, but a stable rhythm that persists over many cycles. It tells us that whatever is shaping the jets is anchored firmly to the body of the object and turns with it, rather than being a transient effect in the surrounding space. The regular pulse, in brightness, is an imprint of a repeating physical configuration. Taken together, the nearly sun-pointing spin axis, the division into permanent day and night hemispheres, the polar switching of jets, the possibility of deep pits acting as chimneys, and the 16-hour brightness rhythm all point in the same direction. 3I. Atlas behaves like a compact, rotating system with internal structure and fixed activity patterns. The details of that structure are still uncertain, but the object does not present itself as a simple lump of ice and dust. It resembles a small, complicated machine driven by sunlight and rotation, with each turn bringing the same features back into alignment and sending out the same narrow streams of material into space. The closer 3I, Atlas, is examined, the more small coincidences seem to gather around it. Directions line up in unexpected ways. Angles fall into narrow ranges. Even the light itself carries patterns that are hard to match with a simple, symmetric cloud of dust. One of the clearest signs of this comes from polarization. When sunlight scatters off dust and gas, the electric field of the light can become aligned preferentially in certain directions. This is what is meant by polarized light. In many comets, the degree of polarization is modest. It varies with viewing angle and wavelength, but usually remains within familiar limits. For 3I, Atlas, measurements show a level of polarization that stands out, higher than what has been seen before in similar objects. This suggests that the light coming from the coma is not just brighter or dimmer in places, it is organized. The scattered photons prefer certain orientations, as if the cloud of particles were arranged in a way that picks out specific directions in space. A nearly isotropic, roughly spherical cloud of dust tends to produce weaker polarization, because there is no strong preferred direction. The high polarization seen here points back toward a geometry that is far from symmetric. The narrow, sun-pointing jet and the overall asymmetry of the coma fit naturally into this picture. A long, thin column of dust, aligned in a particular direction, will not scatter light the same way as a uniform shell around the nucleus. Instead, it imprints its structure onto the polarization pattern. The result is a signal that tells observers, even without a sharp image. That something elongated and uneven dominates the scattering. Polarization becomes one more indicator that 3I, Atlas, is not surrounded by a simple, featureless haze. Geometry also plays a role in the way the object moves through the solar system. Interstellar objects can, in principle, approach from almost any direction. Their home systems are scattered throughout the Milky Way's disk, which itself is tilted by about 60 degrees relative to the flat plane in which most planets orbit the Sun. There is no particular reason for a random visitor from the galactic disk to enter along the same plane that the planets use. Yet, when the orbit of 3I, Atlas, is traced, it lies close to the ecliptic, the plane that defines the paths of Earth and the other major planets. In effect, an object born in a tilted galactic disk has entered the solar system on a track that almost coincides with the turntable on which the planets move. This alignment is not impossible, but simple geometry suggests it should be uncommon. If interstellar objects arrived with completely random directions, only a small fraction would land so close to the planetary plane. Rough estimates put the chance at around 1 in several hundred for any given visitor to match the ecliptic, this well by accident. If there is no preferred orientation, the numbers are imprecise. But the basic point remains. The closer the inclination comes to zero, the more it looks like a special case. So far, only 3 interstellar objects have been observed in detail. One of them, 3I, Atlas, already shows this near alignment. It is not enough to prove anything, but it is one more line on the list of geometric coincidences. The alignment does have practical consequences. Because 3I, Atlas, moves in, or near, the planetary plane, its path intersects regions where planets, asteroids, and dust rings reside. This increases the chances of interesting gravitational interactions and makes it easier to compare its motion with that of familiar solar system bodies. It also means that telescopes designed to survey near the ecliptic are more likely to notice it, which may introduce its own observational bias. An object off-plane could be missed more easily, even if it were present. All these geometric threads spin axis pointing roughly at the Sun. Jets aligned along that axis. Orbit lying close to the ecliptic feed into a larger question. How much of what is seen is simply the result of random orientation? And how much reflects deeper patterns that are not yet understood? With a large population of interstellar objects, statistics would eventually show how often such alignments occur. With only 3 known cases, the margin of uncertainty is wide. This is why it is useful to remember how early this field still is. Before the first detection of an interstellar object, there were no confirmed examples at all. For most of the history of astronomy, all known comets and asteroids were members of the solar system itself. The idea that debris from other stars might occasionally pass through was considered plausible, but remained untested. Once the first visitor was seen, and then a second, the category became real. Now, with 3I, Atlas, as the third, there is still not enough data to define a clear normal for such objects. With only 3 data points, it is difficult to speak confidently about typical properties. Patterns that look striking might smooth out when 100 or 1,000 examples are known. Features that appear unique today might later sit comfortably within a broader distribution. For now, each new object is both a sample and an outlier at the same time. It carries the weight of representing a class, while also being itself. This means that caution is needed in both directions. On one hand, it is risky to assume that interstellar objects must behave like solar system comets and to treat any deviation as suspicious. On the other hand, it is also risky to label every unusual feature as a hint of something extraordinary. The honest position lies somewhere between these extremes, to note the coincidences, to model them carefully, and to acknowledge the limits of current knowledge. 3I, Atlas, sits exactly in this in-between space. Its high polarization, its thin sunward jet, its spin alignment, its persistent anti-tail, and its nearly ecliptic orbit do not let it fade into the background of routine phenomena. At the same time, none of these traits, by themselves, force a single dramatic conclusion. Together, they mark it as an exception, a case that demands patience and precision. As the story continues, comparisons with the two earlier interstellar visitors become more important. By placing 3I Atlas alongside them, it becomes possible to ask which features are shared, which are unique, and how broad the range of behavior among such travelers may truly be. Before 3I Atlas arrived, two other interstellar visitors had already crossed the solar system. Each of them told a different story. Together, they form a small family of guests, with 3I Atlas as the most recent member. The second of these visitors, 2I Borisov, looked very familiar. Images and spectra showed a bright coma and a tail extending away from the sun. Gas and dust streamed out as the object warmed. The chemical composition, while not identical to solar system comets, fell comfortably within known ranges. In many ways, it behaved like a comet that could have come from the outer regions of the sun's own domain. It is useful to imagine 2I Borisov as a distant relative who arrives at the door but behaves like a neighbor from around the corner. There is an accent, perhaps, or a small difference in dress, but the basic manners are the same. Nothing in its appearance forced a rewrite of existing ideas about what comets are or how they move. It was the first clear confirmation that other stars can send comet-like bodies drifting between systems. But it did not challenge the notion of what a comet is. In the landscape of interstellar objects, Borisov marks one end of a spectrum. On that end are visitors that closely resemble the comets already known from the solar system: icy, active, and wrapped in wide, roughly symmetric comae. For this type, existing models of ice sublimation, dust release, and tail formation apply with only modest adjustments. The first interstellar object detected, Oumuamua, occupied a very different place on that spectrum. It showed no obvious coma, no surrounding cloud of gas or dust. As it passed through the inner solar system, careful measurements recorded a small but persistent acceleration that could not be explained by gravity alone. There was no clear sign of jets or outgassing, yet the path of the object deviated slightly from a purely gravitational trajectory. Because of this behavior, Oumuamua was sometimes called a dark comet, an object that might emit gas in a way that was hard to detect, or might be shaped in a manner that produced unusual forces. Its exact nature remained uncertain. Without a visible coma, there were few direct clues to its composition. The increase in speed raised questions that still do not have a simple, agreed-upon answer. It was a bare, fast-moving visitor, leaving behind more debate than data. In this sense, Oumuamua defines the opposite end of the spectrum from Borisov. It shows that interstellar objects do not have to look or behave like familiar comets at all. Some may be inert, rocky, or unusually shaped. Some may interact with sunlight and the solar wind in ways that are still not fully captured by standard models. Between these two extremes, comet-like and almost comet-less, there is room for many intermediate forms. 3I Atlas falls into that middle space, but not quietly. It brings a wide coma and clear outgassing, like Borisov, yet its details differ sharply from typical comets. It displays a narrow jet pointing toward the sun instead of away from it. Its light is highly polarized. Its brightness pulses in a 16-hour rhythm. Its spin axis nearly aligns with the direction of sunlight, creating a permanent day side and a permanent night side. Its orbit lies close to the ecliptic plane, followed by the planets. It is active, asymmetric, and geometrically unusual. While Borisov can be thought of as a comet from elsewhere and Oumuamua as a bear, accelerating shard, 3I Atlas appears as an active, structured system with its own internal logic. The coma is not a simple, round cloud. The jets are not short-lived plumes. The rotation is not random. Each of these features adds a layer to a picture that is difficult to match with a generic comet model. And yet the object clearly does produce gas and dust in significant amounts. Looking at the three together, Oumuamua, Borisov, and 3I, Atlas, one pattern emerges immediately. There is no single template for interstellar visitors. The first shows almost no visible activity. The second looks comfortably familiar. And the third combines active outgassing with strong asymmetry and rare geometries. With only these three examples, the diversity is already striking. This variety has an important consequence. It underlines how premature it would be to define strict rules about what interstellar objects must be like. If more examples are discovered, some may resemble Borisov, reinforcing the idea that comet-like bodies are common between stars. Others may resemble Oumuamua, hinting at a large population of inert or unusual fragments. Still others may share some of the strange traits of 3I Atlas, or introduce new combinations that have not yet been imagined. To capture this situation in everyday terms, one comparison is helpful. Meeting interstellar objects is a little like going on blind dates. After just one or two encounters, any distinctive feature can seem unique. The first person met might appear unlike anyone else, simply because there is nothing to compare with. The second might shift expectations again, with only a handful of meetings. It is easy to overinterpret every detail. The same risk exists here. With only 3 known interstellar visitors, any conclusion about what is typical carries a high chance of being revised later. A feature that seems exceptional in 3I Atlas might turn out to be common once dozens of others are observed. Or it might remain rare, pointing to a special formation pathway or an unusual history. At this stage, the main task is to collect accurate information and keep assumptions flexible. In practice, this means that each new object must be treated as both a sample of a larger population and a unique case. The broad goal is to build a catalog that eventually reveals patterns across many examples. For now, the focus stays close to individual stories: a dark, accelerating fragment, a comet-like stranger, and a complex, jet-driven system with surprising geometry. As surveys grow deeper and more systematic, more visitors are likely to be found. Wide-field observatories, scanning large portions of the sky night after night, will increase the chances of catching faint, fast-moving objects on their way through the solar system. When that happens, 3I Atlas will stand as one of the early markers, a reminder that the family of interstellar guests is varied, and that the first few arrivals can only hint at the full range still to come. If it were possible to hold on to 3I Atlas, this small visitor would carry any passenger out of the solar system faster than any spacecraft humans have ever launched. Its path, already fixed long before anyone noticed it, stretches from the inner regions near the Sun to the faint outer edge of the Sun's influence. From here, the next landmark on its journey is not a planet, but a boundary. Far beyond the orbits of the known worlds lies the region called the Oort cloud. It is not a sharp surface, but a vast, diffuse shell of icy bodies surrounding the solar system. The outer edge, at around 100,000 astronomical units, marks the distance where the Sun's gravity finally weakens to the point that passing stars and the pull of the galaxy begin to dominate. For 3I Atlas, reaching that distance will take on the order of 8,000 years. Over that time, it will pass beyond the known planets, beyond the scattered belt of distant objects, and into a zone where individual bodies are separated by enormous gaps. The sun will shrink to a bright star among many. The familiar constellations will begin to warp as the perspective slowly changes. The object will keep going, leaving behind a system that, from its point of view, grows smaller with every century, measured against human lifetimes. 8,000 years is almost impossible to grasp. Empires rise and fall in a fraction of that time. Languages split and drift. Entire branches of knowledge appear and transform. Yet for 3i, Atlas, this long interval is simply the last part of a much older journey. It has already spent hundreds of millions, perhaps billions, of years moving through the galaxy. The stretch from the inner solar system to the edge of the Oort cloud is only the closing chapter of its brief visit here. Thinking about this timescale turns the object into a kind of clock. If its motion is projected forward, it will cross the outer boundary of the sun's domain around a date close to the year 10,000. Whatever human societies exist then, if any, will be very different from those that first detected 3i ATLAS. The object will still be moving at roughly the same speed. Unaffected by those changes, it links the present to a distant future in a single, continuous line. To see how fast it is really moving, it helps to compare it with something familiar, the Voyager spacecraft. Launched in the late 20th century, they are among the fastest machines ever built by humans. They have already passed beyond the region dominated by the solar wind and entered interstellar space. But they are still far from the outer edge of the Oort cloud. Their speed, impressive by engineering standards, remains slow compared with the velocities common for interstellar debris. Calculations of Voyager's path show that it will need roughly 28,000 years to reach distances comparable to 100,000 astronomical units. That places its arrival near the edge of the Oort cloud around the year 30,000. In that same time, 3i, Atlas, moving faster and starting from an already favorable orbit, will have long since departed the sun's sphere of influence. It will leave the system around the year 10,000. While Voyager is still making its way outward. Set side by side, these numbers carry a quiet message. The most carefully designed spacecraft humans have created so far, using gravity assists and advanced propulsion for their era, are still outpaced by a natural fragment of rock and ice passing through from another star system. The interstellar visitor does not carry instruments or transmit data on command. It does not navigate with intent, yet its speed, set by the dynamics of its ejection and by the galaxy's gravitational field, gives it an advantage that current technology cannot match. This comparison is not a criticism of those spacecraft. It highlights instead how deep the gap still is between human abilities and the energy scales of the wider universe. The objects that drift between stars are part of a much larger flow, shaped by forces acting over billions of years. To move alongside them at their own pace, or to catch up with them once they are noticed, would require propulsion systems far beyond what is now available. From this perspective, the idea of hitchhiking on 3i, Atlas, becomes an evocative image. A scientist once remarked that, if it were possible, riding this object out of the solar system would be more appealing than traveling on any existing probe. The thought is simple. Attach a small payload to an interstellar visitor and let its natural trajectory carry the payload into deep space at a speed no current rocket can provide. In practice, human lifespans are far too short to experience such a journey directly. No individual could climb aboard, watch the planets recede, and stay alive to see the Oort cloud's edge. But as an idea, the image is still useful. It frames 3i, Atlas, as a ready-made transport line, already aligned with the path out of the solar system, already set to cross the boundary where the sun's grip fades. If eyes could remain fixed on it for thousands of years, they would see a steady, patient escape into the wider galaxy, This imaginary ride also emphasizes the value of interstellar objects as carriers of information. Even if no physical craft ever lands on them, they bring with them material from other planetary systems. Their ices and dust encode the conditions under which they formed. Their trajectories trace the gravitational structures they have passed through. In principle, attaching instruments or sample return devices to such objects could one day turn them into probes of both their origin and the space they pass through. For now, the hitchhiking remains a thought experiment. The real work takes place at a distance, through telescopes and models. Yet, the comparison with Voyager and the projected timeline into the far future remind us that every interstellar visitor is more than a curiosity. Each one is an opportunity, moving quickly along routes that would otherwise be out of reach. As 3I, Atlas continues outward, it silently demonstrates what it would take, in speed and in patience, to follow matter from one stellar neighborhood to the next. One day, it may be possible to hold in a gloved hand a small stone that once belonged to another star. For now, the closest experience comes from meteorites that fell long ago on Earth. In northern Argentina, a field known as Campo del Cielo contains fragments from an ancient meteor shower. The pieces are heavy, metallic, scarred by their passage through the atmosphere, and sold or displayed as pieces of a real star you can touch. Those fragments are reminders that bits of the sky can reach the ground. People have grown used to the idea that rocks can fall from space and be collected, weighed, and studied. Museums hold them. Private collections hold them. Yet almost all of these samples have something in common. They come from within the solar system. They are fragments of asteroids or comets that share the sun as their origin, even if their paths were long and complex. The next step is to imagine a similar fragment, but with a different history. Instead of tracing its story back to the early days of the sun, its chemical patterns would trace back to another star's disk. The ratios of elements, the mix of minerals, and the trapped gases inside would all encode the conditions of a distant birthplace. Holding such a sample would be like holding a page torn from another planetary system's early record. A hint of what might be learned comes from a mission that stayed closer to home. A spacecraft called OSIRIS-REx traveled to a near-Earth asteroid named Bennu. It spent years mapping the surface, then dipped down and collected a small amount of material before returning to Earth. The sample weighed around 120 grams. Not much by everyday standards, but enough for detailed analysis in laboratories. Inside that modest amount of dark, fine-grained material, researchers found many of the amino acids needed for Earth-like life. These molecules are not living organisms, but they are among the basic building blocks from which proteins form. Their presence on Bennu supports a picture in which the raw ingredients for life are not rare. Even within a single planetary system, the chemistry that leads toward complexity can happen on small, cold bodies as well as on planets. Extending that idea to interstellar objects leads to a clear question. If a sample could be taken from a body like 3I Atlas, would it show a similar richness in amino acids and related molecules? Or something very different? Would the seeds for life appear to be common around many stars? Or would each system have a distinct chemical fingerprint? Direct answers require more than remote sensing. They require actual material from another system, brought into reach of precise instruments. To move from speculation to contact, a change in strategy is needed. Instead of waiting for data from telescopes alone, some researchers have proposed building an interceptor, a small, fast spacecraft designed to meet a future interstellar object on its way through. Such a vehicle would not target a specific object known in advance. It would wait in a convenient orbit, fueled and ready, until surveys discovered a suitable target entering the solar system. Once an interstellar visitor was detected early enough, the interceptor could be launched onto a crossing trajectory. Its job would be simple in concept and difficult in practice. It would fly out to meet the object, take close-up images. Perhaps release a probe to touch the surface or collect dust, and then either return samples or transmit detailed measurements back to Earth. The goal would be to turn a brief flyby into an encounter rich in information. Seen from this angle, each interstellar object becomes not just a curiosity, but a potential delivery vehicle. It carries material from its home system for free, powered by natural dynamics. A prepared interceptor would only need to match part of its speed and position for a short time. The payoff would be large, the first physical contact with solid matter that formed under another star's light. There has already been at least one situation where such an intercept might have been possible in principle. A spacecraft named Juno currently orbits Jupiter, studying the giant planet and its surroundings. In one thought experiment, orbital calculations suggested that if Juno had retained its original fuel reserves and had been redirected in time, it could have reached an object like 3I, Atlas, on its path near Jupiter. In reality, Juno had already used its fuel for orbital insertion and maneuvers around Jupiter. It was not free to leave its mission and chase an interstellar visitor. The alignment of spacecraft and object was therefore a missed chance in practice. Even if it was interesting on paper, it serves as an example of how the right tool in the right place is not enough if it is not prepared for that specific role. This kind of textbook opportunity highlights a broader lesson. If interstellar objects are to be studied up close, some spacecraft will need to be built with flexibility in mind from the start. They will have to carry extra fuel or use efficient propulsion, and spend long periods waiting in positions where they can respond quickly when a new target is found. That preparation has a cost, but it is the only way to avoid watching each fast visitor pass by just out of reach. Thinking ahead in this way links the story of 3I, Atlas, to decisions about future missions and priorities. Sampling a distant asteroid has already shown that complex organic chemistry can be preserved in small bodies. The next logical step is to extend that approach beyond the solar system, using natural interstellar travelers as carriers of information. To do that, plans for interceptors and responsive spacecraft will have to move from ideas into hardware, ready before the next suitable guest appears on the sky surveys. Not every place that can support life needs the light of a nearby star. Some of the most promising environments lie in darkness, hidden under ice, or drifting between suns. One of the clearest examples is a moon in the Jupiter system. Its name is Europa. Seen from afar, it looks like a smooth, pale sphere crossed by long, dark cracks. The surface is made of ice. Beneath that ice, evidence points to a deep ocean of liquid water, trapped between the frozen shell above and a rocky interior below. The surface is cold and airless, with no open seas or visible blue. But beneath the crust, far from direct sunlight, there may be a global ocean tens of kilometers deep. The ice shell is fractured in many places. Along some of these fractures, something occasionally forces its way upward. Instruments have seen hints of plumes, columns of water vapor and ice grains bursting out of the hidden ocean, rising into space before falling back down. It is easy to imagine what might exist below. A dark ocean, lit only by the faint glow of chemical reactions or warm vents on the seafloor. Perhaps nothing more than simple molecules drifting in the water. Perhaps something more complex, organisms that swim slowly through the black, feeding on chemical gradients rather than sunlight. If any such life exists, a few cells could be caught in the ice near the top of the ocean. Some might be carried upward in the plumes, only to freeze or break apart as they rise. In this view, Europa becomes one of the best candidates for subsurface life in the solar system. It does not offer beaches or skies. It offers instead a stable ocean, shielded from radiation, warmed from within by tidal flexing and possible hydrothermal activity. The cracks and plumes are the only places where the hidden world beneath makes contact with the space outside. sending up small samples of its water and its chemistry. To explore this possibility, 2 spacecraft are on their way toward the Jupiter system. One, launched by a European agency, carries the name JUICE. The other, launched by an American agency, is called Europa Clipper. Both are designed to fly through the harsh environment around Jupiter, where radiation levels are high and magnetic fields are strong. Their task is to study the icy moons, with special attention to Europa and its possible plumes. These spacecraft are not loud emissaries. They travel silently, adjusting their orbits step by step. When they arrive, they will make repeated passes close to the moons, mapping the thickness of the ice, measuring the composition of surface materials, and sampling the thin gases above. Instruments aboard will look for signs of water vapor, organic molecules, and other chemical traces that might hint at processes in the ocean below. In doing so, they become part of a broader effort to search for traces of life beyond Earth, not only on planets in the habitable zone, but in hidden oceans and protected niches. The question is no longer just whether life can exist on worlds like Earth. It is whether life can thrive in darkness, drawing energy from rocks and internal heat instead of starlight. The way 3I, Atlas, carries complex chemistry through interstellar space fits naturally into this wider picture. The molecules in its coma may resemble, in some respects, the molecules in subsurface oceans and on icy surfaces elsewhere. The idea extends even farther. Beyond moons orbiting giant planets, models of planetary systems suggest that many Earth-sized worlds are thrown out of their original orbits during periods of instability. Some collide with other bodies. Others are ejected entirely, becoming free-floating planets. These wander through the galaxy with no parent star, their surfaces exposed to the cold of interstellar space. On such a wandering world, the surface would cool quickly and freeze solid. Any atmosphere might collapse as snow or ice. From outside, the planet would be dark, faint, and hard to detect. But inside, radioactive elements in the core and mantle would continue to decay, releasing heat. If enough water is present, a layer of liquid could remain trapped beneath a thick shell of ice, much like the ocean on Europa, but spread over a full-sized planet. In that scenario, there could be countless drifting Earths in the galaxy, worlds with frozen exteriors, hiding warm oceans underneath, entirely cut off from the light of a star. On their sea floors, hot vents could supply energy to chemistry. Over time, that chemistry could grow more complex. If life arises easily wherever liquid water and energy are present, then these subsurface oceans might be among the most common habitats. From this perspective, the familiar picture of life bathed in starlight becomes only one possibility among many. The universe might be rich in sealed oceans under ice, on moons around giant planets, and on free-floating worlds. Each ocean would be isolated, yet connected to the wider galaxy through slow exchanges of material, impacts, ejections, and the long drift of small bodies between systems. Interstellar objects like 3I, Atlas, fit into this framework as potential messengers. The ices and dust they carry could include fragments from such subsurface environments, altered by time but still bearing traces of their origin. Their chemistry might echo the conditions in dark oceans and beneath thick shells of ice. By studying their composition in detail, it becomes possible to ask whether the flavor of organic molecules in other systems resembles what is seen near Europa, or on icy bodies that have interacted with hidden seas. In the end, the story of 3I, Atlas, does not stand alone. It is one thread in a larger pattern that includes icy moons with buried oceans, deep space missions flying through radiation belts to sample plumes, and theories about planets drifting without stars, warmed only by their own interiors. All of these point toward the same quiet possibility, that life, if it exists elsewhere, may find many ways to endure without ever seeing a sunrise. In the age of artificial intelligence, not only the objects in the sky are hard to decode, sometimes even the voices that talk about them become uncertain. In recent years, whole channels have appeared online that manufacture fake videos of scientists. Their faces and voices are reconstructed by algorithms. Their gestures look convincing at a glance. The background seems familiar. A clock on the wall never changes its time. The words coming out of their mouths contradict what they have actually written or said elsewhere. These clips are uploaded, reported, removed, and then reappear in new forms, on new accounts. This adds a new layer of noise to an already complex picture. Interstellar objects like 3I, Atlas, are difficult enough to understand from incomplete data, limited viewing angles, and short observing windows. Now, on top of that, the public conversation around them can be distorted on purpose. A viewer who searches for information may find a mixture of genuine interviews, careful analyses, careless summaries, and synthetic speeches that were never actually given by the people shown. In this environment, the main adversary of clear understanding is not only measurement error or gaps in the data, it is also deliberate misinformation. A graph can be misread, a number can be rounded carelessly, but a fabricated statement, designed to attract attention or support a fixed narrative, introduces a different kind of problem. It does not simply cloud the details, it changes the apparent intent behind the science. For someone trying to follow the story of an object like 3I, Atlas, this can be confusing. One source may speak calmly about probabilities and uncertainties, another, using the same face and voice, may claim certainty or announce dramatic conclusions that do not exist in the original research. The two versions circulate side by side, and the line between them is not always obvious at first glance. Trust becomes another variable that has to be managed. One simple piece of advice has become more important under these conditions. Look for primary sources. In astronomy, primary data means the original measurements and the papers that analyze them. In communication, it means direct interviews, long-form talks, and written articles where the scientists themselves explain their reasoning. These are the places where ideas are stated in full, with enough context to see how conclusions are reached. The parallel with observation is straightforward. A telescope with a clear, well-polished mirror gives a cleaner image than one with scratches and smudges. In the same way, a mind that relies on unfiltered, original material has a better chance of forming an accurate picture than one that feeds mostly on second-hand summaries and manipulated clips. Short excerpts can be useful, but without the larger frame, they are easy to twist. For the story of 3I, Atlas, this means that anyone who wants to understand the object must, at some point, trace information back to its roots. That might involve reading the published orbital solutions, looking at the polarization measurements, or following the technical discussions of the jet structure. It might involve listening to full-length conversations where the uncertainties are acknowledged, rather than to fragments that present only the most dramatic lines. Artificial intelligence systems, including those that generate video and text, can help summarize and organize information. They can search large archives, highlight patterns, and offer quick explanations. Used carefully, they are tools that extend reach. Used uncritically, they can become something else, a kind of fast food for the mind, easy to consume, pleasant in small amounts, but not enough to sustain a healthy understanding on their own. The analogy is straightforward. A meal of fast food is quick and satisfying in the moment, but if it becomes the main diet, the body slowly weakens. In the same way, a stream of auto-generated summaries and short clips can feel informative over time. However, if they replace direct engagement with complex material. The ability to think deeply and question assumptions can erode. The surface appears covered, but the foundations remain thin. Some educators and researchers worry that a generation raised mainly on such compressed content might lose the habit of wrestling with raw data and long arguments. The kind of careful reasoning that distinguishes between a natural comet and a more exotic possibility requires more than pre-digested answers. It requires attention to detail, patience with uncertainty, and a willingness to hold multiple hypotheses at once while the evidence is weighed. The analysis of 3I, Atlas, is an example of this process. At each step, observations are checked against models. When a feature does not fit expectations, new explanations are tested. The list of anomalies is not treated as proof of any one conclusion, but as a set of clues. The work depends on humans who understand the instruments, the physics, and the limits of the methods. Algorithms can assist, but they cannot replace that understanding. In telling this story, the same spirit applies. The aim is not to offer a fixed verdict, wrapped in strong words and easy certainty. It is to lay out the pieces of information in a calm, coherent way, so that their connections can be seen. The geometry of the orbit, the shape of the jet, the rhythm of the brightness changes. The chemical composition of the coma, the path past Jupiter, and the long escape toward the Oort cloud all form parts of one picture. Against this backdrop, the presence of fabricated videos and careless summaries becomes just another source of background noise. Like interference in a radio signal, it cannot be eliminated entirely, but it can be filtered by returning to original observations, by reading complete accounts instead of only headlines, and by treating automated content as a starting point rather than an end point. It is possible to keep the signal stronger than the noise. In the end, the challenge of understanding 3I, Atlas, is not so different from the challenge of understanding any complex subject in a time of abundant, uneven information. It asks for attention, for a slow pace, and for a willingness to check where each piece of knowledge comes from. The same care that goes into interpreting the light from a distant visitor can also guide the way its story is heard and shared on Earth. There have been moments in the history of physics when it seemed that the major work was finished. Around the end of the 19th century, one of the leading experimentalists, Albert Michelson, looked at the state of his field and suggested that the big discoveries had already been made. In his view, what remained was largely a matter of measuring constants, more precisely, refining numbers rather than changing ideas. The picture of the universe felt almost complete. Only a decade later, that sense of completion began to dissolve. Special relativity appeared, reshaping the understanding of space and time. A few years after that, general relativity recast gravity itself as a property of curved spacetime. Within the following 2 decades, quantum mechanics emerged, replacing the comfortable picture of particles with a stranger world of probabilities and superpositions. What had looked like a nearly finished map turned out to cover only a small region. The contrast is clear. A confident statement about a field being almost done was followed quickly by some of the deepest shifts in scientific thought. It is a reminder that the feeling of closure can be misleading, especially when it is based on what is already familiar. New phenomena, once measured carefully enough, have a way of opening doors that seem to be walls. Debates over quantum mechanics offer another illustration. When the new theory was taking shape, some of its implications were hard to accept. Entanglement, in particular, was described as spooky action at a distance, an effect that went against deeply held intuitions about how the world should behave. One side of the discussion hoped that hidden variables, still unknown, might restore a more classical picture. The other side was willing to accept the non-classical features as part of reality, uncomfortable but supported by experiment. Over time, precise tests favored the quantum view. Correlations predicted by the theory were observed. Inequalities, based on hidden variable models, were violated. The universe did not bend back toward older intuitions. Instead, those intuitions had to be extended. The episode shows that even the most capable minds can be tied, for a while, to patterns of thought formed before new data arrive. Openness to unexpected behavior is not a weakness. It is one of the strengths of science. This matters when confronting objects like 3I, Atlas. The temptation is to fit everything into known categories. Comets that behave like familiar examples. Theories that are already well established. Frameworks that have been polished for years. Yet, a visitor from another star, with a thin jet pointing toward the sun. A nearly sun-aligned spin axis. A highly polarized coma, and a path through the planetary plane, does not slide easily into those categories. A rigid insistence that it must be ordinary would echo the old belief that physics was almost over, just before it changed. At the same time, not every new idea is equally grounded. Some theoretical structures reach far beyond current data, using elegant mathematics to sketch possible extensions of known physics. Models like string theory and supersymmetry explore wide landscapes of possibilities. They offer ways to unify forces, to explain particle families, or to connect gravity with quantum mechanics. But many of their predictions lie beyond the reach of current experiments. When a particular version is not supported, it can often be adjusted, moving the goalposts. There is nothing wrong with exploring such ideas. They map out what might be true if certain conditions hold. The difficulty arises when the link between theory and observation becomes too loose. A framework that can bend endlessly to evade falsification loses some of its power as a description of nature. It remains an interesting mathematical construction, but its connection to the world stays uncertain. The situation with 3I, Atlas, is almost the opposite. Here, the starting point is not a grand theory, but a set of direct observations, images showing a narrow sunward jet, light curves with 16-hour cycles, spectra with unusual chemistry, polarization measurements that do not match ordinary comets, orbital data that place the object on a near-ecliptic path. Any explanation must answer to those facts. The data cannot be reshaped to suit a preferred narrative. Instead, models must adjust to match the behavior actually seen. Looking ahead, the amount of such data is likely to grow quickly. In Chile, a new observatory equipped with a 2-gigapixel camera is preparing to survey the southern sky repeatedly. Every few nights, it will scan large sections of the heavens, catching objects that move, brighten, or fade. Projections suggest that, once in full operation, it may detect a new interstellar object every few months, instead of one visitor every few years. There could be a steady stream. In that future, interstellar objects will no longer be rare curiosities. They will become a regular part of the observational landscape. Some will likely resemble known comets. Others may look more like Oumuamua. A few might share the peculiar traits of 3I, Atlas, or introduce new ones. With such a sample, the question of whether 3I, Atlas, is an outlier or a representative of a broader class can finally be answered. Patterns will emerge from numbers, not from impressions. In parallel with this scientific expansion, thoughts turn to how societies might respond if truly unexpected findings appear. One suggestion is that the discovery of clear technological activity beyond Earth could shift priorities on a planetary scale. If evidence of advanced systems elsewhere were confirmed, the motivation to invest heavily in space infrastructure telescopes, interceptors, warning networks might grow dramatically. Budgets that now flow into military hardware could, in principle, redirect toward planetary defense and deep space exploration. In that scenario, investments on the order of current global military spending, even reaching into the trillions of dollars per year, would not seem extravagant. They would be treated as necessary steps to understand and protect a small, fragile world in a much larger setting. Whether such a shift will happen remains uncertain. But the possibility connects the path of a single interstellar visitor to broader questions about how a civilization chooses to use its resources. Behind all of this lies a simple image, a pale point suspended in a beam of light. When a distant spacecraft turned its camera back toward the solar system and took a picture, Earth appeared as a faint blue dot, less than a pixel in size, caught in a sunbeam scattered by the optics. Every conflict, every boundary, every history unfolded on that tiny spot. From far away, arguments over territory and pride shrink until they are hard to see at all. Interstellar objects like 3I Atlas pass through this scene without slowing down. They cross the plane of the planets, curve around the sun, and head back out. Carrying with them material from other places, they do not notice the thin film of air around one small world, or the species that has begun to watch them. Yet that species, from its vantage point on the pale dot, can measure their paths, analyze their light, and use their brief visits to test its own understanding. In that sense, 3I Atlas is more than an unusual comet. It is a reminder that knowledge is still expanding, that closed doors in physics have a history of opening again, and that the view from a small planet can reach far into the dark between stars. The story it leaves behind is quiet, a collection of data points, a set of questions not yet fully answered, and a gentle shift in perspective. Small, but real, against the vastness that continues to unfold. As 3I Atlas continues on its way, it does not carry answers with it. It carries distance. It carries time measured in millions, perhaps billions of years. Its passage through the solar system was brief, quiet, and largely indifferent to our presence. Yet, within that silence, it offered something rare, a chance to observe matter shaped far from our own star, moving according to rules older than human curiosity itself. Nothing in its motion demanded urgency. Nothing in its behavior required fear. What it asked for instead was patience, careful measurement, and the willingness to accept that nature does not always fit familiar categories. Objects like this remind us that discovery does not always arrive with clarity. Sometimes it arrives as a collection of small irregularities, faint signals, and unanswered questions. And sometimes that is enough to expand the boundaries of understanding. Thank you for spending this quiet time exploring the universe with us. As we look ahead, more visitors will come, more data will gather, and more surprises will emerge from the darkness between the stars. Until then, the sky remains open, and the story continues.